last semester know how it works. So this is my university website. It's seeklab.com, and if you go to teaching 459, yeah, you will, because I was logged in before, you will not. I don't have a password, but I didn't have to re-log in. But the password is GoPower 2016. GoPower 2016. Okay, so that's the password that's recorded in this video, and I'll upload the videos after the class. So after every class, I'll upload the videos to the website. So yeah, the website, we'll fill it up as we go along. So it will have everything we need related to the course uploaded to the website. So it does not, because I was a little late. I got this up last night. So bear with me. But people that took my course last semester know that I do fill it up very quickly and get the right material up onto the website. Yeah. So the syllabus is up there now, so you can download it, and it's also on Howdy. I put it last night. So okay. So we'll go, skim through the course syllabus just to get an idea of what the course is about, and then maybe look at a few interesting animations, maybe, and get started with the course, right? So the course, as the description says, discusses. I'll have to sit next to the computer a lot because of so the audio is clear when in the recording. So the course generally discusses transmission and distribution of electrical energy as related to power systems, and the way it discusses that is by tackling every component of the power system. So starting from the generation until the load. So we study each of these components individually, and then we build up a system. And we don't go into too much of the theoretical detail of every single component, except the transformer, maybe. So the transformer we spent a little bit more time on, because it's a very special component in a power system. You probably, if you've taken 338 before, so you've probably studied transformers in quite a bit of detail. How many people have taken 338? 2, 3 people? Okay, so the transformer section may have a little bit of a review for people that took 338. The people that didn't take 338, we will we'll start it from the beginning, and we will emphasize things that are relevant to the power system. So in 338, you probably will not discuss the different transformer connections, right? So the different transformer connections affect their performance in the power system. So so besides in 338, you typically will deal with the transformer as a device that steps up or down voltages and currents, and you would draw the equivalent circuits. We take it a little bit more into the power system application. So and see how transformers are used to change phase shifts and how phase shifts affect design of the power system. So the background that we will need really is the 214 or 215 course. Yes, it may be a surprise to some, but it really is the basic of electrical engineering. The basis of electrical engineering is this simple 214 stuff, right? So the AC circuit work that you did at the end of 214 is the basis of the course. So you should be able to, for example, I didn't connect the pen. That's why I was trying to write this and move this thing along, and it didn't work. Ooh. Now what do I do? Okay, now. So, for example, this is something you studied in 214, correct? And this should be something that's familiar to everybody. Does everybody feel comfortable with something like this? So this is a like Vmax sine omega t type source, and this is L, this is an R, another R. Everybody's okay with this? Adobe wants to update, we will not. How about if I do something like this? People are okay with this as well, correct? So here, for example, what would you do to find the current in this branch? What's the quick procedure? Yeah, just Ohm's law. But what would you do? So you would find the equivalent impedance, right? So these two are in parallel, and these two are, and then these two are in series, and then they're in series with the parallel combination of this impedance. So you have a voltage source and basically equivalent impedance here, right? And then you found the current coming out of this source, right? And then you can can use Kirchhoff current law and nodal analysis, etc., to find the current here, to find the current here, etc., correct? And if I remove this capacitor, the equivalent impedance will change, right? If you put it back, equivalent impedance changes again. What does a capacitor do to the angle between voltage and current? What does, yes? Excuse me? Lags? No. It will change the angle between voltage and current. Yes. So maybe I didn't ask the question properly. So, for example, you have a voltage waveform that is like this. If you have an equivalent capacitive impedance, what will the current look like? Assuming it's a linear circuit, of course, so the current will be sinusoidal. Okay, so what will the current look like? No, exponentially drop. That's that's when you have an equivalent impedance that is capacitive, and you have a DC source, and you are turning a switch on or turning a switch off. In that case, if you have an equivalent capacitive circuit, what will it look like in steady state? Capacitors are what in steady state? Short circuits or open circuits? Capacitor impedance is what? XC is 1 over j omega c, right? So for DC, a capacitive impedance looks like what? 1 over 0 is infinity, right? So it's an open circuit. So for DC circuits, for a DC steady state condition, a capacitor is an open circuit. So if you have a DC source here, and you have an equivalent impedance that looks like a capacitor, RC, whatever, but it's more like a RC type circuit, right? So the equivalent is more capacitive than inductive. In that case, if you have a switch here that you close initially, there will be an initial transient if the capacitor is not charged, right? So yes, there will be some exponential rise in current, right? Or exponential rise in what? What will the exponential rise in what? What will exponentially rise? Actually, not current. Huh? Exactly. So the voltage across this capacitor, if you have a capacitor here, for example, the voltage across the capacitor will rise exponentially, right? Why is it doing that? Because you're taking current from the source and dumping into the capacitor. So the capacitor is charging. But capacitor current changes instantaneously, right? So you'll find that the capacitor current changes instantaneously and starts charging the capacitor, right? And then decays exponentially, like Khaled was saying, until the capacitor voltage reaches the source voltage. In that case, there will be no more current flowing, right? So that's in DC circuits with transient switching switching analysis. Yeah. In AC circuits, though, in an AC circuit, if the voltage is sinusoidal and the impedance is a passive impedance, a linear impedance, then the current will also be sinusoidal. Okay, so let's agree to that. So if they're both sinusoidal, something else is happening to the current in the circuit where the equivalent impedance is capacitive. What will the current look like? Will the current look like this? It will be what? It will lead. Yes. So if you look at, for example, IC equals, okay, what's the capacitor current equals what? C dVc by dt, right? So if the current through a capacitor is equal to the differentiation of voltage across the capacitor, right? So what is the differentiation of a sine wave? A cosine, right? So assuming the impedance is a complete capacitance. So if it's a cosine, then it's going to look like something like this, right? No. Right? So this is one period of the current waveform. So now this is the current. Where is its zero crossing? Somewhere here, right? I mean, this is continuous, right? It wraps around. So current in this case is leading the voltage with some angle theta. What do we call that angle? Hmm? It's a phase shift, but what is it called in power terms? Maybe at the end of 214 you took that a little bit. The power factor angle, have you heard of that? So you've heard of that? Okay, so this is called the power factor angle. It's the angle between the voltage and the current, right? So if the impedance is an equivalent capacitive impedance, the current will lead the voltage because of this equation, right? And the angle between the zero crossings is the power factor angle. How about if it's an equivalent inductive impedance? Voltage will lead because current will lag in that case, and we will have something that looks like this, for example, right? So in this case, voltage is leading this current waveform. Yeah. So basically, this is what we are going to reduce our big power systems to. So we're going to reduce it to a simple circuit like this that you've studied in 214. Right, this big power system. We'll show you some pictures of nice big power systems, and they will look so complicated, and you will think, wow. And then you probably how many people interned in a power system sort of facility or industry or factory, or have seen a big power system of an industrial plant or of a country, or nobody? Okay, so we'll show you some. We'll show you some, and they will look so scary, right? And then what the idea of this course is to reduce them to something like this. Really, that's what we're going to get to towards the end of the class, right? But to reduce it to something like this, we have to, okay, how do I take a generator and reduce it to something like this? And how do I take generators of different ratings and generators in different places in the power system and put them all together and make them all, build a small interconnected circuit this way. Even though one generator may be at 10 kilovolts, and so I maybe have a generator here, for example. This is in real life, this may be a 100 kV generator, and in real life, this may be a 10 kilovolt generator. How can I be putting them both into the same circuit and doing Kirchhoff current law at this node, right? It's just bringing them into this same picture is what we're going to study. For example, this circuit here can look like a power system that we can draw right now. So this, what we drew was, okay, we had this, and we had our load here, right? This is a single phase circuit, right? I can tell you that this is something that would represent maybe a generator. And this here is what we call a bus bar, right? And this section here, we will eventually figure out how to make, those transmission lines that are strung between towers. We will make this represent the transmission line impedance, for example. And this we will make represent, actually, I mean, complicate it a little bit more. Let me add another inductor here and tell you more. So this inductance here, for example, we will make represent a transformer, right? And then this resistance here, we will make represent your house, for example, right? So this is a power system. It's a power system single line diagram, right? So this is what it's called in practical power system terminology, a power system single line diagram. And we will take this and figure out how to make it look like this in this course. That's really what the course is about, okay? And then, what if, for example, I don't know, Khalifa buys a new house and puts it here, right? Let's say, okay, so Khalifa buys a house and puts it here. And then, who's a troublemaker that won't mind? Eric, you're okay if I say that you burned down your house? Okay, so Eric burned down his house. Okay, so I'm picking on you today, but it's fine. We'll be friends by the end of this month. It's fine. So Eric burned down his house. Okay, so if Eric burns down his house, I mean, this is a very hypothetical situation. Okay, I don't know how he burned it down, but so there would be, for example, there's a potential that the electrical cables coming into his house, for example, become shorted, right? So you have, for example, 3-phase coming into your homes. For example, if the house burns down, the insulation on the cable breaks down or melts, and 2 terminals touch each other. Or one of the terminals of the 3 phases that are going into somebody's house, for example, touches the ground wire. Is that a normal case or an abnormal situation? It's an abnormal situation, right? So these abnormal situations, we have to figure out a way to detect and protect against, right? Why did I add Khalifa's house here before talking about Eric burning down his house? Because if Eric burns down his house, Khalifa doesn't want to be affected, right? So we will have to be designing protection systems that will isolate Eric's house, in this case, where the faults are, right? And not interrupt service to this house, to this load, right? So that's something we will do towards the end. But before we do that, right, these abnormal cases are something we will have to deal with mathematically in the middle. So mathematically, it's not as straightforward to convert a system like this when it's operating in normal conditions to a simple circuit like this. So we will use a mathematical tool in the middle of, towards the last few weeks of the semester before we talk about these protection systems and faults to allow us to convert systems with faulty cases, faulty conditions, to simple circuits like this. So at the end of the day, all we're doing towards the end of the course, from the beginning until the end of the course, is dealing with circuits like this. Right? But to get to a circuit like this in abnormal cases, we will have to introduce some mathematical tools as well. So this is something we will do. What else? Okay. I think this summarizes the whole course. And then we will deal with this. We deal with this. We build these models in a power system simulator as well. So we will deal with a simulation tool called PowerWorld. I'll show you some interesting things about it right now, and we'll look at how it's interesting and useful. Can you simulate something like this in what simulation tools have you used before? Multisim, for example. Have people used Multisim before in 214 for simulation, for example, of simple circuits? SPICE? Well, yeah, SPICE, Multisim, whatever you've used, right? You've used an AC equivalent circuit simulator, whatever it's called. You can simulate a circuit like this, sure. But there are some power system terminologies that are interesting that only the power system simulators would include. And there are certain things that we want to study. For example, these failures that occur. Power system simulators are equipped with the ability to study these failures. So when you build a big power system, do you want, for example, let's say a failure happens here. So we said we'll take this guy out, right? How about, what if a failure happens here on this line? If a failure happens here, is this load or this load going to receive power? So in this case, everybody loses power, right? So this is a small system, and it's easy for us to imagine what's going to happen here. But what if you have a system, and this system has what? This has one node, or bus in power system terms. It's bus. But this is nothing but a node here, right? In your circuit, this is a node, right? This is an impedance, and then after this impedance, there's a node, right? So this is this other bus here. I put a transformer here. This transformer, there's a node behind it, right? Where are these transformers located? Does anybody know? Right before your homes. Where does anybody know where these things are located?
Step down.
Yeah, in the U.S. is different. So where are these located on the step in the U.S.?
Like I saw them in the neighborhood where, like, I recognize the step down because I can tell that one is reducing power.
How can you tell it's reducing
Because
voltage,
it's in
not
front
power?
of-
It
I
is
mean
not.
voltage, yeah.
Voltage or current. Transformers step up or step down, voltages and current. They don't change power. Theoretically speaking, there's a power loss, but it's an ideal, theoretically ideal. Let's assume it's ideal for now. So how would you recognize it? You cannot recognize it from outside. You cannot recognize if the transformer is step up or step down. You will see sometimes in the U.S. the transformers, the distribution transformers that are close to your homes, most of them are pole mounted. So they'll be on a pole here, and it's like a small tank up here mounted to the pole, right? And this tank will have, some funky looking, horns, whatever you want to call it. So these are insulators. So they're electrically insulating bushings of the transformer is what they're called, right? So you would have terminals coming in, and you would have smaller terminals, coming out, for example. You have some smaller ones and some bigger ones. The bigger ones are probably where the high voltage is coming in. The smaller ones are where the low voltage is coming out, right? And their job, these insulators, which we will study a little bit further down the road, their job is to basically, if this cable here has a potential on it, a voltage on it, and the housing of this transformer is connected to the ground potential. So there's a big voltage difference between the two. So if there's a big voltage difference between any two devices, do you want to bring them too close to each other? Why not? No.
Inducing.
No, not induction. No. Why don't you want to bring two electrodes with very high voltage difference between them close to each other? Yeah. What is the why? How? When do these arcs form? If you have air where these electrodes are located, at what voltage would they form? If you have two electrodes 1 centimeter apart in air, what's the voltage that will break down the air? No, 30 kilovolts. Yeah. The breakdown voltage of air is 30 kilovolts per centimeter. Right? So air is a dielectric, right? Which course is that when you study dielectrics? Is it 322 or 322? So air breaks down at 30 kilovolts per centimeter. So you bring two electrodes with a 30 kilovolt voltage difference, 1 centimeter apart, and they will cause an arc. Move them, 1.2, assuming this air has no humidity. There are certain conditions for the air. Okay, I don't know them at the top of my head. Assuming certain conditions for the air, then the arc will not occur. Okay, so definitely you don't want to bring a conducting terminal here close to something at a very different potential because of the potential of the arc. So these bushings are insulators that protect against arcs occurring. So you need to keep some distance. And of course, practically, you're not going to bring them, even though these voltages are not close to 30 kilovolts, right? You still don't want to bring them too close because, again, we're not talking about air now. We're talking about, rain. We're talking about dust collecting on these insulators, right? So these insulators have a body with a certain shape. This shape has some treacherous path that is designed so that it is treacherous for anything to build up on it. And the materials are selected such that they are difficult for anything to stick on it, right? So you have these insulators that have bodies, for example, that look like this, where the high voltage terminal is coming in here, and then it's going into the transformer. The transformer chassis or body or whatever will be typically grounded or connected to the neutral wire. We'll talk more about that. When do you connect to neutral only, when you connect to ground. We will have a nice section discussing that as well at some point, yeah. So if something builds up here, if dust builds up here, and then you have some dust, and then some water, some fog, some dew, blah, 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 and then you have a nice conducting path for electricity to flow, then this conductor here will be connected to the chassis of the transformer, right? So these conductors these insulators or bushings are there to prevent that, right? So in the US, distribution is mainly pole mounted. I would say 95, 98% of distribution is pole mounted, especially in Texas. Texas is a big rural sort of community, right? So land is big, homes are very far apart, etc., etc. So most transformers are pole mounted because it's cheaper than digging cables, right? So if you have to dig underground and put all these cables everywhere for very long distances, it's very tough. But of course, you come into a big city like Houston downtown, right? You're not going to have distribution on poles, pole-mounted transformers with cables everywhere, because it's not something nice that people like to see, and because of space considerations and limitations and safety issues, etc., etc. So for example, has anybody driven by the Ras Abu Funtas plant lately? Ras Abu Funtas power plant here in Qatar. You know where the old airport is? If you take that road towards the new airport, you will pass by the Ras Abu Funtas power plant, right? If you've driven by this place maybe 7 years ago or 6 years ago, you would have found lots of transmission towers. Lots of transmission towers. There's a big power plant there, right? So the transmission, this power plant has generators, right? These generators generate electrical power, and then actually I should have put also another impedance here. I'll put another impedance here because typically there's a transformer associated with a power generator. I'll talk about that later shortly. So after this transformer, so I generate the electrical power, and I would step it up. Why would I step up power before transmitting it a long distance? So this is a generator and then a transformer. I'm saying this is a step-up transformer. And I'm saying what happens after that is this is the power plant, for example, and then this is my transmission line, transmitting power far away to an electrical load. Why would you step up voltage before transmitting it? Exactly. So it's power loss, right? Power loss in an electrical system is I squared R, right? That's at the end of the day, there is no power loss associated with the ideal inductor of the transmission line. So, but the transmission line is a piece of copper or a piece of aluminum or a combination of both, right? And we will talk about different types of power lines. In that case, it has some resistance, right? So this resistance will burn power. Of course, the nice thing about transmission line, resistances is, we know that resistance is equal to what? Rho L over A, right? The resistivity divided by length divided by cross-sectional area, right? The nice thing about cables that we can just hang up in the air that are typically used to transmit power. Okay, so transmission is typically going to be on using these transmission towers, and we will talk about different types of towers also in the course. Yes, ma'am.
Resistance is directly proportional to length,
Rho L over A. Ah, sorry, rho L over A, not rho L over A. It's rho L over A. Sorry, I apologize. Yeah, you're awake. It's good. Munazza is always awake. Yeah. Okay, so yeah, it's rho L over A. So yeah, forget about L, but yes, it's proportional to length. This has a resistivity, and it's inversely proportional to area. That's the topic I'm trying to discuss now. So if it's inversely proportional to area, what would I like to do to a transmission line? Make it very small or make it big? The diameter, make it large as possible, right? But if you make it very large, it becomes costly. What else? Also, what does it become? Light. It's heavy, right? So it also becomes heavy. So if it's a heavy cable, so you build something that has infinitely low resistance or a very small resistance, so that you can reduce power losses. But it's this big, right? How big of a tower do you need to carry 3 of those? Huge towers, right? Very expensive towers, lots of space, etc., etc. So it's an optimization problem, right? So we're always going to be optimizing in a power system. We're always optimizing. So voltage levels are going to be something that you will decide based on an optimization problem. Of course, people have settled on certain voltage levels in a power system based on experience and optimization over the years, etc., etc. And we'll talk about what we have in Qatar here shortly, and similar information about what's going on in the US as well. Yeah. But yes, the idea would be to make them large. So you cannot make them too large. So you make them, large enough so that the resistance is low, so you don't lose a lot of power through the transmission process. Yeah. So that's an important consideration. So these transmission cables would be also bare. You would if it's hanging on top of a transmission towers. Are you worried about somebody holding onto it? You're not worried about it, so you're not going to add an insulator jacket around it. You're not going to add something to insulate, big, heavy, insulation around on the whole transmission tower cable, for example, from the power plant all the way to the industrial facility in Ras Laffan, for example. You're transmitting power there. Why put an insulator? It's going to be a bare insulator. So it's bare copper. It's a bare conductor, copper or aluminum. We'll talk more about that. But of course, before you connect it to the tower, you will hang it from an insulator as well. So you will hang it from one of these insulators as well. We will talk about that later. So you will hang these cables from these towers and transmit the power. So you want to make the voltage as high as possible. How high? The highest voltage we use in Qatar is 400 kilovolts, right? So that is the highest transmission voltage. Okay, so now if we are transmitting at 400 kilovolts, do you think the generator is generating at 400 kilovolts? Why not? Sure, there is a step-up transformer. Why? Well, I can just make a generator to generate at 400 kilovolts. Why not? We said we're making the transmission cables as large as possible, right? So that it can withstand this the current that's coming out, and we keep them spaced from each other so that we can not break down the air between them and cause an arc or flashover between the conductors. So if you're transmitting 3 phases, we keep these large insulators, we space them accordingly. If you drive along from here to Al Khor or Ras Laffan, you will see these transmission towers with the cables spaced. They're not very close to each other, they're certain spacing so that they don't flash over, right? So if I'm trying to take all of this, I'm trying to generate the same, if I put the current from the generator straight into the transmission line without stepping up the voltage to reduce the current, without putting the transformer in the middle, that means that I have to operate at that same voltage that the transmission line is operating at, as well as push current. If I want to push that same current the transmission line is pushing, right? If the same current coming out of the generator is going to have to go through that transmission line at the same voltage level, then and the generator is a lot smaller in this case, right? The luxury I have in the transmission line is I can space the conductors, I don't know, a few meters apart, right? How about in the generator? The generator looks like what? You typically have what? You typically have a stator with some teeth. right? And you have a rotor, for example. Let's talk about the synchronous machine rotor, for example. Just 2 poles, and you would have, for people that studies 338, this is how Dr. Haytham represented the synchronous machine, right? And there will be windings here. And these windings will be connected in a certain fashion. We don't care about that in this course. They will be, current will either be coming in or out of these windings, depending on the way they're connected, right? So all of this is very close to each other, right? And these conductors, if I'm gonna remove insulation from around them, right, and I'm gonna have to keep big space between them, then I'm gonna have a huge machine, right? The generator will be huge, humongous, right? I cannot tolerate, I mean, if I'm gonna have these windings operate at 400 kilovolts, at certain terminals of the winding, so this winding may have a voltage difference between it and this winding of 400 kilovolts in that case. For example, look, that's not, we have to get in a lot more detail before I can say that, but let's say there's a full voltage difference between these 2 windings. They cannot be so close. They cannot be so close. And these windings are typically, these windings are typically actually coils. So you would typically wind it like this, for example, and this would be one terminal, this would be another terminal. So let's say this is one terminal of the winding, and let's say this is another terminal of the winding. So there are lots of these wound, and then you take this coil side and this coil side and put them in a slot here, and put this one in a slot here, for example, right? So these are right next to each other. They have to be insulated. You cannot put them next to each other if they're not insulated. The job of this is, if you go back to the DC machine theory, right? You probably studied DC machine theory where? Also in 322 maybe, where you would, looking at, for example, if you have a coil in a magnetic field, in a time-varying magnetic field, and you have current, if you push current through that, equal to I, and what's going to happen? This is a magnetic field, time-varying magnetic field. What will happen? Voltage will develop here. Or if you put voltage here, right? Voltage will develop here. So voltage will develop if you have what? If you rotate this, if you rotate the coil in a time-varying magnetic field. So if you rotate, this is a magnetic field. If this is a magnetic field, and this is just a turn of coil, right? If this turn of coil is rotated in this magnetic field, then this coil will see a time-varying magnetic field cutting it, right? This is, the coil has a cross-section that's perpendicular, for example, to the magnetic field in one direction. Then you turn it around. Then it will see the different components of the magnetic field will change, right? If you turn the coil against the direction of the magnetic field, then the vertical component that's intersecting it is not perpendicular to the coil anymore. There's a different component of the magnetic field that's intersecting with the perpendicular to the coil. So the coil will see a time-varying magnetic field, right? If a coil sees a time-varying magnetic field from Lenz's law, remember this equation, E equals n d phi by dt, right? If a coil, here n is 1, because I have one coil, right? If I have a time-varying magnetic field that's cutting a coil, voltage will develop across the terminals of the coil, E. If voltage develops across the terminal of the coil, I take this and I connect it to a resistance somehow, then current will flow, right? So the whole idea is each of these turns in the coil is creating a voltage. So they're all in series, right? So I'm taking this is a series loops of turns, bunch of turns. So this is one turn, right? This is one turn in series with another turn here, in series with another turn here, right? So these are 3 turns, for example. Each of these turns are spinning, for example, in a magnetic field. So generators, how do generators in a power plant run? Generators in a power plant, for example, and we will show pictures of power plants later, but the basic concept is you will have some turbine that's driven maybe by steam. So you would take maybe coal and burn it, and this coal would be used to boil water and convert it to steam, and this steam will be pushed into a turbine that has blades, and these blades will turn the turbine, the mechanical prime mover, right? That mechanical prime mover will be connected to an electrical generator, which is this. This electrical generator that's connected to the mechanical prime mover will turn this basic winding, this single winding. If it turns this basic winding, and let's say you have magnets, right? If you have magnets that are creating this magnetic field, so if magnets are creating this magnetic field, a prime mover is turning this around, then you will have voltage generated, right? So in this case, the magnets are resembled by this winding. So this is called the field winding of a synchronous machine. This is called the field winding of a synchronous machine. So this is what's creating this magnetic field. And then this magnetic field, if I'm rotating this, then I'm rotating the magnetic field around. So each of these coils here, these coils that are in these slots, are seeing a magnetic field. So this is the prime mover is moving this around. If the prime mover is moving the magnetic field around, then this magnetic field will pass by all these coils at different times, right? And it will provide or link these coils differently at every instant of time, and hence generate a time-varying magnetic field, and hence generate a voltage across the terminals of the wind. Okay? If this variation is sinusoidal, for example, then I can generate a voltage that's also sinusoidal. Correct? So I can create a sinusoidal voltage across my windings. This is a simple explanation of how a synchronous machine works without getting into details, because we don't care about too much of the details in this course, right? Moral of the story is these are insulated wires. You cannot make them at 400 kilovolts. For you to make two wires that are close to each other at 400 kilovolts, we said the breakdown of air is 30 kilovolts, right? For 1 centimeter, breakdown of 1 centimeter of air is 30 kilovolts. So 400 divided by 30 is what? 9, 8, whatever. 7. So I would need to make sure that I keep each wire, 7 centimeters apart from the next one, because you don't know. Again, when you wind these things, the first one will create a voltage. Next turn will create another voltage. Third turn, and then you add all these voltages, and that's what you see here. So if the terminal voltage of each coil is 400 kilovolts, in the same slot I have a very low voltage, and I have a very high voltage as well. So you have a wire, coils or turns that have generated a very high voltage, and ones that have generated a very low voltage right next to each other, right? So you cannot do that, right? So you'd have to insulate them significantly in that case. Can you do that inside the machine? Otherwise, if you do that, you can do it. Theoretically speaking, you can, but it becomes enormous, right? If you build an enormous machine, it's going to cost enormously, right? The cost will be enormous, and not just cost. Forget about cost. You cannot even move it. Yeah, you cannot move it to location. And some of the problems with power system components is it's very difficult to move. Yeah. So, has anybody, for example, look? The building behind city center, not the one that they're building now or they're almost finished building. Behind it, there's a big building that says Kahrama on it. Does anybody know that? The first, I think half the building. You know what's in half the building? A transformer. I'm serious. So they have 2 transformers just in half the building. So they have, just take a look at it next time you go. Half the building is a transformer. So these things are huge, and I will get you a transformer data sheet. I'll put it on the website, and we'll talk about how big these things are and how difficult to move. So again, it's very important to consider the fact that you have to optimize the size of these equipment. Yeah, and a transformer is easier to make big than a rotating machine, right? A rotating machine has a lot more failure prone, right? This is something rotating. Bearings, and can you imagine if it fails? Removing the rotor from inside the stator and repairing it, it's a big deal. Trying to change bearings, for example, right? With a transformer, fine. Something has to be high voltage, right? So the step up side of the transformer, that will have to be coils that are gonna have to be insulated for the full voltage, for example, right? But the primary side isn't. So okay, we're good. We're happy. We try to save something there. At some point, we're gonna have to connect to the 400 kilovolts, right? And insulate against 400 kilovolts voltages, right? So, but do we want to do that inside the generator? No. It's much more difficult to repair a generator than repair a transformer, right? Transformer is a static device. Okay, you unwind the core. We look at how cores look, and you create these big bobbins of wire outside, and install them, for example. It's much easier than taking a stator out of a rotor and shutting down your whole plant and all of that to do it, right? And transformers would be cheaper devices than a generator, right? So that's why we have to step up. And this whole discussion is about why we step up, right? So we have a generator. This generator typically will be connected to a bus bar. This bus bar will typically be connected to a step-up transformer. And then we transmit power. After we transmit power to the location where we need power, we would typically step it down. Okay? Would we receive power here in Qatar Foundation, as much power here in Qatar Foundation as Ras Laffan city would use or consume? Probably not, right? What kind of loads do we have around Education City? Lighting, air conditioning, very limited, right? We don't have big machines or motors or processes or whatever, right? So we are probably not going to be consuming as much power. So since we won't be consuming as much power, we don't expect to invest a lot in our power system as much as these other guys would expect to invest, right? So why am I saying that? Because typically a large producer like RasGas, for example, or the Ras Laffan city, they would let's say that we're generating here at between 8 and 20 kilovolts. Generators would, that's the voltage levels of the generator rating here. Let's say between 8 or 20 kilovolts, depending on the generator. And then we step it up. We step it up to, let's say, 400 kilovolts. In Qatar, we can step it up all the way to 400 kilovolts. There is a 400 kilovolt network in Qatar. And we would transmit. After we transmit, we get to Ras Laffan. At Ras Laffan, for example, big consumers in Ras Laffan will have their own, Kahrama will have a deal with them. Tell them, okay, you take power at, for example, 132 kilovolts. We'll sell you power at 132 kilovolts. So what does Kahrama have to do? Step down the voltage from 400 kilovolts to 132 kilovolts. And then Kahrama says, okay, guys, you take it from here. You take it from here. We have a contract with you that we will deliver this much power at 132 kilovolts. And you have an obligation on power factor, right? Because power factor depends on what? The load, right? We said that the power factor depends on whether the equivalent impedance on the load is capacitive or inductive, right? So typically Kahrama would say, okay, I have an obligation to deliver power to you at 132 kilovolts, and this power has to be clean, and we'll talk about what clean means. And on your side, you have to make sure that you don't pollute my power. And we'll talk about what pollute my power means. And if you study power electronics, you would know that pollute means you make the current waveform not sinusoidal, right? So we saw lots of non-sinusoidal waveforms when we studied 438, right? So we would expect that a consumer like RasGas would have a lot of drives and, for driving the compressors, and, motors are starting and stopping. So lots of variations in the shape of the current, et cetera, are happening. This is pollution to the current, right? Kahrama doesn't like that, right? So they will have a contract with RasGas, say, okay, we'll deliver this power to you, this amount of power at this voltage level, and your obligation is to make sure you don't pollute it and you maintain power factor at a certain level, etc., right? And then Ras Laffan city or RasGas takes it from here, right? They're taking power at 132 kilovolts. We cannot do that here. We are not doing that here, or we're not doing that in our homes. Kahrama then goes further and says what? Okay, I'm going to go to Education City. So Education City, they will have They will take, send a cable. For example, this is a transmission line hanging on towers, right? And this is one tower, another tower here, transmission lines here, right? Then they came close to Ras Laffan. This is maybe another transmission tower. Now they're inside Ras Laffan city. Then this is probably going to be what? Underground cables. From here, I don't think if you go inside Ras Laffan city, I don't remember, but I haven't been there in a while. But I don't think if you go inside Ras Laffan city, you will find transmission towers. You may find only at the entrance by the time it comes in. And then everything will be distributed underground, right? So they would distribute that using underground cables. Okay, so then what? Then there's a transmission tower here as well. This transmission tower took power from this 400 kilovolt network, and they brought it, I don't know, where's the closest tower that I've seen here? Maybe, Tariq Shamal, the highway, the Doha Expressway, there are a few transmission towers there, and then we don't see them anymore. After that, everything goes down, underground. So, at some point, for example, they've, had transmission towers, brought them close enough where, I don't know the closest location for the transmission tower to the city center, for example, but at some point, they transmit power on transmission lines, then they bring them down through cables to some substation that would have a transformer. This transformer is, for example, going to feed some homes or some area inside the city, close to city center. The transformer at city center, in this building that's taking half the building, I believe that is 66 kilovolt to 11 kilovolt transformer, right? So what does that mean? It means that here, if I'm saying this is 400 kilovolts, that means that I should have added another area here where I took this 400 kilovolts and converted it to what? Yeah, but before that, actually there's a 400 to 200 typically, because we have a 200 kilovolt network. So some people will be taking power at 200 kilovolts. And then there is a 132 kilovolt network in Qatar. So 200, and then there's a 132 kilovolt network. And then from 132, I will typically have a transformer from 132 to 66. That's before this one that's in the building behind city center, right? So there's a series of transformer, right? And Kahrama manages all of these, right? So they will be and then there are consumers at different voltage levels. The bigger consumer you are, the higher the voltage level you will probably take power at, because it's going to be cheaper for you. Why is it going to be cheaper? Because you're going to invest in building your own power system. Kahrama will sell you power at 132 kilovolts. Ras Laffan City, you take care of yourself, right? Until it gets to what? So this is 11 kilovolts, right? This is the 6611 that is in that building, right? 6611. Then what happens? Then we get to your homes, right? Your homes are consuming power at what voltage? What? 240 volts, yes. 240 volts phase voltage, right? So we're talking about three-phase system. So what would be the line-to-line voltage from three-phase? What would be the line voltage? If 240 volts is your single-phase voltage, what is your line-to-line voltage in three-phase system? Take this, multiply by square root of 3. We will review that, but I just wanted to make sure some people are aware. So 240 square root of 3 is going to be about 480 volts, I think. Right? So that's 480 volts. So this transformer now 6611, that's the big one behind in the building city center. And this will be 11 kilovolts, 11 480 volts. 11 kilovolts, 480 volts. And so this would be the line-to-line voltage, be 480 volts. So now if you take a single phase of that, then you get your 240 volts at home. Okay, so this is a whole big chain of transformers. And again, yes, sir.
And the 11K to 480 transformers, are they located like inside our houses? Or?
No, not inside your houses. In the US, I said these are pole mounted. It's a good point. In Qatar, we don't have any pole mounted transformers. We have, if you drive in your neighborhood, you will find a small building somewhere. Yeah. And this small building is a substation as well. So anywhere there's electrical equipment inside will be called a substation. Okay? And typically what you will have there is nothing but an incoming feeder, Okay, this is the terminology the power system guys use, right? So it's an incoming feeder, and you will have a bus bar, right? And then you will have a transformer, and then you will have a bus bar, and then outgoing feeder. In addition to that, you will have all the protection equipment and communication equipment that go along with that, right? So you may have a circuit breaker here, circuit breaker here. You may have some protection devices we will talk about. Maybe here. Okay, so there may be some communication radios, right? Why we will have we'll talk about that as well when we talk about protection. So sometimes, to protect an area, there is no way for you to, let's say, for example, you want to protect this cable, right? And this cable is 10 kilometers long. How would you protect it? One way to protect it is measure current here, right? And measure current here. If there's a difference in current, what happens? That means that there's a problem somewhere in the middle, right? If the current here, this is a cable, right? The current has to be the same. There's a voltage drop across the cable, yes, right? But the current has to be the same. So if the current has any deviations from the beginning to the end, then this is an indication that there's a problem in the middle somewhere. Maybe it's a small leakage or capacitive current, or we'll talk more about that later as well. Again, if you have any potential difference between devices, then you have a capacitor, right? So if you have something at 1 kilovolt, and you have a piece of metal as well at ground potential, then even though you don't have a physical capacitor there, this is equivalent to a capacitor. You have 2 plates, 2 points, 2 nodes with voltage difference. What is this voltage difference is isolated by a dielectric, air, sand, whatever it is, right? Then it's a capacitor. It's a huge looking capacitor, funky looking capacitor that you didn't pay for or you don't like, but it's a parasitic that is going to be in the system, right? So we will study actually this and figure out how to calculate these capacitances. Maybe something you did in 322, so we will probably review that, right? So if there is an equivalent capacitance somewhere that is drawing some leakage current, right? If this is a capacitor and it's a voltage here, current will flow, right? There will be this is an capacitive impedance at a certain frequency. Then there's a capacitor. Then capacitive current will flow, right, to the ground. So you will allow for things like that. You're a designer. You know that your cable has an equivalent series inductance. It also has an equivalent shunt capacitance. So you will know, okay, I will allow for certain deviations, right? And that's how you set your protection system settings here. So, but if these 2 points are very far away, how would you deal with this? Add a communication system, right? Have somebody here, a radio here, talk to a radio here, right? So typically we have in the power system microwave links or fiber optic links, right? And that's why it's important for communications engineers to understand how a power system operates, right? Because they're very critical. I mean, the idea of protecting a power system cannot happen if you don't have these radio links that are used to protect the system, or the fiber optic links that are used to protect the system. So there's a lot of communication system or communication engineering work for people working in the utility. So the utility does not only hire electrical power engineers, right? Communication systems are a very integral part of a power system. And this big buzz that we hear today about smart grid and blah, 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 all of it is not, they're adding more sensors. And when you add more sensors, that means you have more data, that means you have more reliance on the communications engineering and the communication equipment, right? So the communication engineers are creating job opportunities for themselves. We've always run power systems without a problem, right? But now, add sensors, add communication systems, and now we can hire communications engineers. They didn't have jobs before, so don't tell Joseph Boutros about that or Khaled Karaki. But no, this is critical, right? So it's important. Communication engineering is an important aspect of the utility. So it is important to know what signals are going to be sent from here to here, and why, the frequency of sending those. So if you want to study protection in a lot of detail, we will not. We will study the basics of protection towards the end of the course. But if you really want to study protection in a lot of depth, you will have to get into the communication systems that are associated with a utility. So what did we draw here? What? A generator, a bunch of nodes, right? a bunch of transmission lines, a bunch of transformers, some loads. Is it any different from the circuit that I mean, if you take this, okay, now can I draw the equivalent circuit for all of this? It's a big mess, yes, I see a big mess here, yes, but this is nothing but something like this. Generator, transformer, transmission line, another transformer, a load. I took a tap, I took a voltage, I connected to this node. I have a transformer, I have another load, I have another transformer here, another transformer here, another transformer here. So what? Right? And then I connect, and this is a load as well. So this is, let's say, a resistive load, let's say a resistive load, let's say a resistive load, right? And then how do I solve this? Finish, I take this, right? Connect this here, connect this here, connect this here. Can you solve this or not? Loop equation, loop equation, loop equation, right? Simple, right? So this course is very easy. This is the course. This is what we do in the course, with a little bit of deviation, with a little bit of considerations for power system terminology and okay, how do you find the value of this? Okay, you have the transformer nameplate. It's a 20 MVA transformer with voltage rating, blah blah blah, connected this way, etc., etc. The tedious part is okay, taking this nameplate data from a real transformer and converting it to a value that you plug into this circuit. Seriously, that's really the whole story. Okay, so I didn't even go through the syllabus, but I think you can go through the syllabus. So this is the textbook you have. So I summarized everything so I have 2 more minutes. So I'll summarize, I'll go through the syllabus quickly. So we are going to obviously use, differential equations and complex variables. Again, anytime you have AC quantities, you have angle, magnitude and angle, right? So we're going to obviously use complex variables and complex numbers to analyze our system. And we will have sets of equations, right? You have these loop equations in the circuit. So you will have to use linear algebra to be able to solve them. We will definitely build, you have 10,000 nodes. Of course, I'm not going to give you a 10,000 node problem in an exam, right? It will be a 2-3 node example, right? But power systems people, they deal with thousands of nodes in the circuit, right? So these thousands of nodes, how do you deal with them? You put them in a matrix form. We will show you how to put them in a matrix form. And then there's a lot of people working on, okay, matrix algebra is very interesting, right? If your matrix looks a certain way, you can divide it up and chop it up and put zeros and do interesting things about with the matrix to simplify your calculations, to speed up the process, right? So we have very fast computers now, but we still want to speed up the process even further to be able to simulate larger and larger systems, right? So we will have to use matrix computations to understand how to build the system and set it up in a matrix and solve a set of linear equations using a matrix. And all of this is, of course, using AC signal, AC equivalent circuits of the system. Yes.
Can we use our TI calculators?
Yes, you can use your calculators. I have no problem with you using your calculators. You will have a lot of fun inverting matrices and all of that stuff. Yes, sure, you can use your calculators. That's why they're there. Yeah. So definitely, I will have a review of 3-phase. I understand that we need a refresher on 3-phase, so we'll go through that. And then, as I said, we're going to take every single component and see how to put it in the equivalent circuit. So we'll start with our transmission line, I think. Yeah, we'll start with our transformers, but maybe I didn't. I flipped the order here. So we'll look at the transmission line, these transmission line cables, and then figure out how to model them and put them in the equivalent circuit. The objective will always take the real device, find an equivalent circuit, put it in the simple model that we have that will look exactly like what I drew, right? And then do the same thing with the transformer. Find its equivalent circuit, plug it into, find its equivalent circuit and the parameters that from the nameplate data from the real transformer, plug it into the circuit. And then, okay, you've taken all this stuff and plugged it into the circuit. The circuit, these devices were all at different voltages and were different power levels, etc., etc. How do you make them interact? Okay, this will be using a normalization of the system. So you will find a way to normalize the values and ratings of all these components. Because if you're dealing with an 11 kilovolt transformer and a 5 kilovolt transformer and a 20 kilovolt transformer and a 30 kilovolt transformer, you want to put all of those in the same circuit, same single circuit that I drew, right? How do you do that, right? You have to find a way to normalize, right? If normalization is a great thing, everything will look like what? 0 to 1. You know 1 is big, 0 is small, right? So if you find a way to normalize the values of all the quantities that you have, you will be able to plug them into the circuit, which will be a normalized circuit, right? So that's what we will do next. So we'll figure out how to do that and then put all of them into the circuit. And then we will have a fancy name for solving the circuit in power systems is called power flow analysis, right? That's the fancy name for loop equations, right? We will talk more about power flow analysis, but it's nothing but loop equations. And then, if there is a problem and somebody burned down his home, Eric is a responsible person. I will not pick on you anymore. Engineer Adil is your lab coordinator for this course, so he burned down his home, sorry. So we have to deal with him, right? So we have to find a way to deal with these special situations. So this will create an unbalance in the system. This unbalance in the system, we'll have to deal with it in a certain way. So we will talk about that, which is points 7 and 8 and 9. And after we deal with the different components and how they are represented in an unbalanced fashion, we will figure out a way to now take these unbalanced representations of these components and build a simple circuit like we did, simple AC equivalent circuit as well, which is what we will do in point 10. And in this case, we will call them sequence circuits. Instead of equivalent circuit, we'll call it same, but it's the same voltage sources and impedances, but they are the ones that represent these burn down problems or these problems here. And then, of course, because we have these problems that we have to protect against, so we will talk about how to protect a system like that, and all of that you'll be able to simulate using simulation software, right? So this is the summary of the course. Please go through the rest of the stuff. We will touch upon it next time. It has all the information that you need. I did not finalize, but February and April will be the exams. We'll have 2 exams and a final during the course. I'll talk more about homeworks and quizzes. I do a lot more quizzes, so we will balance that out, and I will discuss that policy. But everything is in this in the slides, in the syllabus. So please go through it, and next time we'll continue. I hope you got a picture of what the course is going to deliver, right? And this is really what we're going to be doing throughout the semester. So I'll stop here. If you have any questions, please drop by. Office hours are there for myself and Adil. They're listed in the syllabus as well. But again, you can drop by anytime or send me an email anytime. I have no problem with that. Yeah.